So, Thomas and Gerhard
Thank you, Max.
from Flexoptix will tell us things about optics we would like to know. How to get to 800 gigs. There you go.
Okay.
Perfect.
Thank you very much, Max. My name is Thomas Weible, co-founder and CTO at Flexoptix. And together with Gerhard, our lead research engineer, we have one topic with us about reliability testing in the network, where we think is quite of interest because when we see people building networks, they typically, when we're coming from the optical side, they plug in their transceiver and their network gear, and then the first tests are basically, okay, we look at the power levels. When they are fine, we bring the link into production. Now, there are other effects which can take place, and that's actually part of the presentation today, that you can do more testing instead of just looking at the power levels. And the term we are talking about is about bit error rate tests. And that's the talk about. And the power, how we can use the transceivers for that one. So yeah, I move on. The talk is a little bit separated in a couple of sections. I do a little bit of intro at the beginning and a recap to get everyone on board. And then we jump straight into the bit error rate dependency. What is the, where is it coming from? And we saw in our lab, we saw effects on the distance and also on the temperature, how it can positive or negative influence the bit error rate. And then Gerhard is performing a live demo, how we can do the testing straight out of a transceiver, just with the management interface of a transceiver without any router or switch behind it, and some takeaways. Okay. Let's start. First of all, last year we gave a presentation, it was Gerhard only, not me, about coherent pluggables, and also we introduced, which we think is quite new to the data point of view, like people like you building networks. The data point of view is more like the bit error rate, but there is also the signal to noise ratio. When you talk to the optic folks building WDM networks, their main concern is the signal to noise ratio. And what is the signal to noise ratio? It's straightforward. This is this graph in the bottom here. We got the noise level on the bottom, and we got our desired signal, that's the peak, and we basically want to have in the optical transmission a big margin between the peak and the noise level. Like in this audience now, everyone is quiet, we have a great SNR, a great signal to noise ratio, and the PA does the rest to understand it clearly, hopefully. But as I said, the bit error rate is more for data folks doing telecommunication there, and we will see later on there is a relationship between the signal to noise ratio and the bit error rate. Now, going even further back in time, and even Liam mentioned this in his talk about submarine cables, about the tiny pluggables. So when 400 gig was introduced back in 2019 in a pluggable form factor, not in the big transponder cards, a new thing came into the pluggables, the digital signal processor. This tiny chip basically covers a couple of functions, and the main one we want to talk today is about how we can run a bit error rate test inside of that DSP, and also how we can analyze the signal to noise ratio straight out of the DSP. So actually that's the chip who is holding, or the firmware who is doing all the magic there. Okay, so what did we test? We tested a couple of transceiver pluggables. All of them have a DSP inside, and when we start at the bottom with the 800 gig ones, like a DR8 doing 500 meters, what we tested there. Also looking at the latest development on 400 gig up to a QSFP 112. What is so special on QSFP 112? It is the next generation of the QSFP DD, but more on the electrical side. On the electrical side, we have 4 lanes running 100 gigabit instead of having 8 lanes doing 50 gigabit. That's the major difference between QSFP DD and QSFP 112. And then also the coherent for sure, and like a garbage product out of the 400 gig development are the 100 gig single lambda transceivers. So these 100 gig single lambda transceivers do have a DSP, but they only have one lambda, one wavelength carrying our 100 gigabit. And as we have the DSP, we can do further testing there. Okay, so we're gonna show the results. We don't show all the results because this would exceed until in the afternoon. We don't want to exceed our slot too much. So we just picked out certain results where we think is worth to mention. And the first one is about, as I said at the beginning, on the distance. We took a 100 gig QSP28 ER1, sorry, doing 40 kilometers. We used a couple of fiber drums in the range or span distance of 10 or 20 kilometers, and we cascaded them to different lengths. And to make it really precise, because we wanted to reach the edge cases, we also used attenuators. The main goal is there to protect the receiver for sure, but also on our setup, we wanted to reach the edge cases. And the important thing here is when we look at the specs of the transceiver itself, we mainly focus on the receiver. So the receiver has a minimum of minus 14 dBm, and that's actually where we want to get close to, because we identified then and also saw that the minus 14 dBm is somehow the edge case, and if we are close to that, what's going to happen there? Yeah, this was more on the theory part. I think that's basically it for that one. And now to the results. So we run the tests straight out with the Flexbox. Gerhard will show it later as well. And on the transceiver, we hooked on the management interface, captured the temperature, and combined all the results on different cascades from 2 meters up to 50 kilometers. And there is a demarcation line up there. Because on the y-axis we do have the bit error rate, which is 2.4 multiplied by 10 to the power of minus 4. And that's actually the demarcation line of bit error rate. You don't want to get below that one, because otherwise you have way too much errors, and then it's causing troubles, and you can't correct them later on any longer. That's a definition by IEEE. So we want to have a better bit error rate than 2.4 multiplied by the 10 by the power of minus 4, and for simplification I just use the exponent now for further slides, minus 4, minus 5, etc. 2 meters up to 40 kilometers were straightforward. They were in the range of a proper bit error rate, and the interesting one is the 20 kilometers. And why is it so interesting? Because it's close to the edge, to our demarcation line of not proper bit error rate any longer. And then when we look at the Rx power, we are still almost within the specification of minus 13 dBm, but we are really close at the edge there. And that's actually the root cause why we are almost hitting that curve. You can even see it on a higher temperature. We are below that one. And to have the proof there on the 50 kilometer, we were really out of spec of minus 14.6 dBm, and you can also see it on the curve. The 50 kilometers went out of the rooftop. You might wonder about those question marks there. This is more effect of the implementation on the firmware. So what happens while the transceiver is operating? The temperature increases, and then there are correction functions which correct the transmitter's bias going through the transmitter, and then optimizes the TX a little bit, and you can see a drop there every time. It's made basically on a lookup table, and the bit error rate increases then a little bit when it hits a certain temperature then there. Okay, this was on the distance. Some words about a bit error rate in general. So this is this nice formula behind that. It's straightforward mathematics. We have the bit error rate there. We have the number of errors in general. We cluster them typically, so assume 100 errors. This is based on Gaussian noise. It's a proportional distribution function there, and you divide it by the overall bits in a certain period of time you transmit it, so the total amount of it. So when we assume 100 arrows and a speed of 100 gigabit, and now looking at a really bit error rate link with a bit error rate of -12, which is per definition a bit error free, then we have a gating time of those clusters, of those 100 errors to each other, of roughly 16 minutes. So, and the forward error correction will take care of that one. Now, when you decrease the bit error rate down to -4, which is our demarcation line there, the gating time gets really shortened down to 4 microseconds. So these clusters will show up every 4 microseconds, and the forward error correction has a way harder job and needs to perform way more workload than when the link is running at -12, just to get those figures there. Okay. Now, as I said at the beginning, beside the distance, we also looked at the temperature. And the temperature, for sure, we also had to tweak a little bit. We had to get, first of all, rid of the lid of the Flexbox itself, and then plugged in, that's actually a coherent module, and we added a heatsink and also some fan to blow off the heat. And the funny story here is, we took the heatsink actually from an old Cisco 800, so there is somehow 25 years of history matching together, running on a coherent plug, which is pretty awesome. And the side story here is a good friend of mine. He does the commission in Frankfurt area, and he takes out all kind of equipment in Frankfurt data centers, and he rips it all in part, and he handed it over to us. And with that, I hand over to Gerhard.
Thank you, Thomas, and welcome. Let me continue with the coherent cooling, which is a little bit simpler compared to the direct detection one. Do we have laser here? No. Okay. Sorry. We don't. It's that one. Okay. Doesn't matter. As you can see, we don't have the jumps anymore, and the lines are more or less constant. The reason for that is, with the coherent, we have the advantage that we have more parameters we can work with. Our DSP is looking at the polarization, it has the phase shifting, and with that it has more opportunities to correct the signals away, and the power that you get way smoother lines. They are not perfectly constant, but it goes there, at least according to the temperature. If you use different fiber lengths, obviously you get different bit error rates. What is more interesting is the range of that we have 10 to power of -2 and -3. That's a different specification, because the thing is, the amount of parameters, it's like with the control circuits. If you have more parameters, you have more ways to correct your signal. And here, the coherent transceiver is a little bit more tolerant. That's the reason why coherent transceivers, at least this low power one, also can deal with higher distances. Here, the attenuation was not required, and that's a big advantage. So let's get to a little bit more hands-on, since we are more interested in edge cases like high temperatures. Usually you don't run a transceiver at 120 degrees. Here you can see I made it in Microsoft Paint, so you can still see with the different colors it's some aluminum foil with the Flexbox below it, but on top the transceiver, so it is exposed to heat. This heat gun can go up to 600 degrees, so don't use it for any other things other than electronics. And we wanted to see what happens. And I did it in 4 phases. First without heat gun, so that was just the warm-up. Since we have some thresholds, like the 65 degrees is a very good, I could say, golden point for most of the transceivers. Because some transceivers have different vertical lines of high alarm and high warning. Some can run up to 90. In this case, this one is below 80. But we wanted to see what happens if you go beyond these vertical lines, because you might have seen it on your network gear. So with that, we went up to 100 degrees. I removed the threshold, tried again with 100 degrees. And then I wanted to see, after having done that, if the transceiver recovers itself. So The signal gets lost, yes, but afterwards, when I reboot the transceiver, let it relax, cool down a little bit, does it still work? I will get back later to a different experiment, but here, as you can see in the cool down curve, we are hitting what was before the 100 degrees, so the bit error rate is still the same. This transceiver survived the 120 degrees. I think that's an awesome thing. But let's get to our live experiment, which is a little bit more interesting. We don't have so much time. And this guy, since it's very small, it's a little bit time to boot. There we go. Yep. Let's give it a little bit of time while I explain what we are seeing here. So we already talked about bit error rate. A second page, media SNR, which is the fourth diagram, pages on the memory. They are shared between both of them. So what we usually are doing here is writing into a certain section of the memory where we swap between SNR. So you might wonder maybe a little bit why the FPS is not that good. The reason behind it is that in the background it's swapping. You're going to see it in a brief moment. It's still booting up. It's almost there. And yeah, I mean, we are also checking RX power. We're also checking temperature. Here we go. And yeah, it starts booting up nicely. The bit error rate starts high since it is a counter that is being considered. It goes down because more data transferred. It's checking how many errors were transferred. So it's getting stable. The temperature obviously goes up. This transceiver is getting a little bit warm, but not so bad. And RX power is something to look forward for. I mean, it is the thing you usually look for if you want to have optical signal. And media SNR is a relationship between signal and noise ratio. So these are the two views. And if we want to get this curve a little bit smoother, we can disable the swapping of pages like this. And you can see now the curve is a little bit smoother. That is one thing you have to keep in mind, because if network gears are accessing the transceiver, sometimes they have to write those diagnostic selectors, they are called. And to really prove it's not a pre-recorded video, I'm going to bend the cable like this, and it's scaling, auto-scaling itself. And the lowest point, you might have seen our application or any other OPM, the lowest value is usually 40. Here we go. Now we are out of signal, and the bit error rate goes to 1. It jumps up. And the SNR is also interesting. You don't want to go below 20. It almost went below 20. Then it jumped up, like the signal would be better. But as we learned in the previous presentation, SNR should be in a certain range. If it is beyond 30, it is bad, because we have the effect called shot noise or quantum noise. It is like a spread of photons. You don't want to have this in your fiber, so you have to be in between those. And 30 is a value that usually is set when the signal is not good anymore, and below 20, it's getting worse, right? Yeah, and that's it with a little experiment here. Here's a little live demo. So that is what you can expect from our transceivers, or one of those. Let me shut this down and get back to our material. Second experiment, this time with 250 degrees, and let's see if this transceiver this time recovers. And this is how it looks after you applied this temperature. So you cannot even read the label anymore. This guy was quite hot. I'm not showing the whole diagram. There's something more to the right you don't see, but it's not interesting because it was loss of signal. I added another scale, a horizontal line. I called it weird. You are not going to see this on your network gear. My own idea, because you start seeing negative temperatures when you go beyond 128 degrees. Our developers might know why. It's related to the first bit that is a sine bit. So I corrected here in the graph. But yeah, I mean, beyond that, getting to 120, the transceiver stops working. I was able to boot it up afterwards, but the reception signal was way worse. So this transceiver is basically unusable. And with that, we broke one of our transceivers. you have to sacrifice at times. And yeah, basically some takeaways. And as our first speaker mentioned, slides require some sort of AI. So we decided to generate a picture and with a little bit of summary. So bit error rate on direct detection transceiver depends on both temperature and fiber length. Look for that. Bit error rate is the rolling average. I forgot to mention that more. You have counters, how many bits were transferred, and you have counters, how many errors were transferred. You divide it. But what you're really reading is a bit error rate. If you read it again and you had bad values, it's basically dragging the history. So it's a rolling average value. And yeah, I mean, between higher alarm temperature, don't try to trespass it because the margin is not so much. If you go like 10 degrees more, most likely you're losing the signal. Thomas.
Okay, and what Gerhard also previously showed when he heated up the transceiver to 120 degrees, you might have seen the 80 degrees where we got the loss event with the transceiver having the DSP inside. So we actually were not able to get to 120 degrees because the DSP has a safety function inside. So when it's getting too hot, it's actually shutting down. And then you get a loss. And that's the point where you're going to look at your gear anyway because the link is gone. So that's more a safety function, which is quite helpful also to protect the DSP. Otherwise, it's broken. The coherent ones are a little bit more, let's say, ruggedized, just to the effect of the properties of light. Beside of just having the amplitude, we also have the phase and the polarization. So this combination of that signal makes, this combination of these three characteristics of light makes the signal more ruggedized. And so we are less sensitive to the temperature at all. But don't get me wrong, on temperature changes. But when we exceed the overall temperature, then for sure we are running into issues. And yeah, finally, as said at the beginning, there is a relationship between the signal-to-noise ratio and the bit error rate. But when you operate in a data center or in a co-location, direct detection transceivers, or formerly known as the gray transceivers, there is not much you have to bother about the signal-to-noise ratio because when your bit error rate is fine, the SNR is also fine. And that's, I think, quite helpful. That's it from our side. Thank you very much. And we are happy to take questions.
Are there any questions? I don't see any.
I can answer the next one. There will be lunch now.
No, no, no. There's something between this and lunch. No,
Okay.
no. There's no lunch.
Sorry.
Not yet, not yet.
Not yet.
Not
Okay.
yet.
People are hungry already.
Well, okay, then thank you very much, Thomas and Gerhard.